Okay, minasan, konnichiwa, Zamurai Engineer desu. So in this live stream lecture module, we'll resume our discussion of compression members. So let's start with global buckling. But before we proceed, let us confirm the sound check. Confirm the sound check. Okay, thank you for confirmation. Okay, konnichiwa. Okay, therefore let's proceed. So these slides are brought to you by AISC, American Institute of Steel Construction. It is developed by Scott Sibian of University of Massachusetts Amherst. So our courtesy is for this organization and for Professor Sibian. So first, individual columns, and we will start with global buckling. So squash load. So there are three failure modes in compression. So we have squash load, global buckling, local buckling. So squash load, fully yielded cross section. So when we have this type of building, we call this as squash load. When a short stocky column is loaded, the strength is limited by the yielding of the entire cross section. The absence of residual stress, all fibers of cross section yield simultaneously at the force over area is equal to the stress. Okay. So very basic theory and compressive in its manner, as you can see on the diagram. So all fibers of cross section yield simultaneously at that. So that is our theory. Uniformly, simultaneously, the cross section. So in your figure, you are actually seeing the member that is W shape, okay, W beam or W shape section. Okay. Residual stresses results in a reduction in the effective stiffness of the cross-section. A continuous accumulation, very little by little residual stresses, but the ultimate sparse load is unchanged. A reduction in effective stiffness can influence onset of buckling. Okay, so if the effective stiffness is decreasing, it has what direct effect on starting of buckling. With a residual stresses, plans tips yields first at force divided by area plus residual stress. So there is another term. So now the theory is P over A is equal to Fy, but now we have something additional, that is residual stress. So gradually get yield of entire cross-section. Gradually, little by little, it accumulates. Okay. Stiffness is reduced after first yield. So, as you can see on the diagram, supposed to be there's no residual stress. Okay. Here, so P over A here, still there's no residual stress. So, as you can see, I will temporarily turn off my video device so that you can see the cross section. So yielded steel. So although the theory we have the uniform application and the overall cross section, but you can see the yielding of steel will start at these flange edges. Okay. So we are now on this part, around this part. Okay. So we have these edges that yielded ready. Okay. Then on the 2, so included some areas of the, so you will notice that the edge yielding increased, okay, and also we have what yielding in the web part. Okay, so this is the point 2. Okay, so point 1, point 2, and point 3, we are now on this part. Okay, so actually the diagram look like this. Okay, this is the ideal, but the actual would be like this. Okay, so 3, we have increased, another increased yielding on the cross section. So notice that this would impact the buckling later on because of this yielding. Okay, and 4, part 4, we have what? We have total cross section, all yielded. Okay, so every particles on the cross section experience yielding. So we are now on the top. Okay, on the top. So let us now talk about the Euler buckling. So Euler buckling, what happened? It returns. So Euler buckling assumptions. Column is pin ended. Take note. Pin connected at its end. Column is initially perfectly straight. Load is at centroid. So very normal. Obviously, we already use this type of assumptions. Material is linearly elastic. Okay. No yielding as yet. Okay. Member bends about principal axis. Okay. So no twisting. And plane sections remain plane and the small deflection during. So these are the assumptions. Okay. So no twisting as yet. So in order for us to tackle the global or Euler buckling. So Euler buckling, therefore, pin connected, top and bottom, pin connected. So we have the delta, capital delta here, okay. And then we have the Euler force is equal to pi. This is pi, not phi, okay. So this is the constant value, the mathematical constant popular value of 3.1416. So this is pi squared. So Euler force is equal to pi squared EI over L squared. Okay. So we have the stable equilibrium, then afterwards bifurcation point, then go horizontal. Okay. So again, this is the stress strain curve showing the value of modulus of elasticity, which must be used here. You have to be used here. Okay. And what else? Depending on I minimum, meaning the inertia, and L squared. So that so therefore, if you have this delta capital delta here, so meaning to say it is very much dependent on L. You can feel it as the L becomes shorter and shorter. So the force would provide us greater and greater amount of force. Okay. That's why it is dependent on L squared. Okay. And also dependent on I. As you can see, okay, I here, because I is also dimension. Okay. It has direct relationship with the dimension of the material. If the dimension is bigger, then the amount of force that it can carry will become bigger. And as the length become higher, okay, the length become higher, the amount of force that it can carry will become shorter and shorter, or lower and lower, okay, independent of uh, yield strength. Okay, so independent of yield strength, of course, there is no yield strength here. Okay, so yield strength, okay, it is only dependent on I, L, and E. Okay. So, but E is the type of material which we already have a constant because we are using steel. For similar unbraced length in each direction, minor axis, IY and AW shape will control strength. Okay, so So for minor axis IY, so we have here minor axis, major axis. Okay. So similar, same, but the point of view, the direction, axis, uh, point of view, different. So we have this. Okay. Either point of view, we have constant L. So, but we have different inertia with respect to X, with respect to Y. Okay. We can rewrite in terms of stress. So, Euler force equal to pi squared DI L squared divided by A. So, divide both sides by A so that we can uh, have the following: pi squared DI over A L squared. Then R squared is equal to I over A. So this is the radius of gyration. R is the radius of gyration. So if you want to use the radius of gyration, then you can have this formula. Okay, I over A is equal to R squared. So therefore, we can say R squared to the numerator, then L squared denominator. Therefore, we have what? L over R quantity squared. Okay, so, and L over R is now what we call slenderness ratio. So let's define this one, L over R as slenderness ratio, SR, slenderness ratio. Okay, slenderness ratio will become higher if the column is longer. Okay, so it is more slender. Okay. So therefore, we have used the Euler buckling stress. This is now a stress, not a force, because force divided by area, we have the stress. Okay, so Euler stress. So when we divide everything by area, so force is pi EI over L squared, stress pi squared E over slenderness ratio squared. Buckling controlled by largest value of LR. Most slender section buckle first. Of course, it is quite logical and to be expected. So the largest value of slenderness ratio, the more it is susceptible to buckling. Most slender section buckle first. Okay. So this is our diagram of stress versus slenderness ratio. As you can see, go back to your this is the formula. Okay. So stress, this is the stress, is inversely proportional to the squared. So it is not only inversely proportional but to the squared of the slenderness ratio. So you can see the curve is more pronounced in this area because of that. Okay. Okay. So for Euler assumption regarding the actual behavior, initial crookedness or out of straight. Okay. So cap delta 0. This is the initial midspan deflection, as you can see. Midspan deflection. Okay. That is cap delta 0. Okay. As you can see here, This is cap delta 0. Then apply the force. So you get what? An amount of moment because of this delta. Okay. Okay. So initial crookedness. Okay. So we have the Euler up to that point. Okay, then it will go that way. Okay. So although this is the ideal model, so the actual would be the red portion. Okay, so it's the red portion. So it seems that the model line, so straight, vertical, and horizontal, are the asymptotes of the actual diagram. And to this, because of area, the actual area, we already know this from several still diagram. We have the actual behavior if we will use the actual cross-sectional area, because the cross-sectional area will change. Okay. So regarding this initial crookedness assumption, buckling is not instantaneous. We are limited by this matter, by this assumption. Then additional stresses due to bending of the column. Okay, so we have the straightaway initial stress plus minus MC over I. MC over I is the flexure, okay, due to bending. So flexure meaning bending. Okay. Assuming elastic material theory that never yields, P approaches the Euler. So the Euler is the limit, okay, the maximum that the material can handle without yielding. Okay. So after which the material will substantially yield. Okay. So as you can see here, so without yielding up to this point, then it will yield here. Okay. Then actually some strength loss, small delta, cap delta 0, small loss in strength. As we can see on the diagram, large delta 0 strength loss can be substantial. Okay. So if you depending upon the amount of delta 0, okay, because it will become bigger the moment here, bigger, the loss will become substantial. ASTM limits of delta, so L over 1000 or 0.25 in 20 feet. Typical values L over 1500. So typical values L divided by 1500 or 0.15 inches in 20 feet. Okay, that is the ASTM limit. Okay. So next is about load eccentricity. So if our element experience like this, so as you can see, we have the same discussion of this. So the actual, so we just repeated. So load eccentricity assumption. Okay. So, if a moment is significant, section must be designed as a member subjected to combined load. Okay. So, the same assumption, but since eccentric load, okay, so we must take care of the eccentricity. So how much is this delta, cap delta 0? Okay, cap delta 0 is too large. Okay, so eccentricity, so as you can see here in the previous crookedness consideration, as you can see here, delta 0, but here now E refers to eccentricity. This is eccentricity. They are the same, but now we are considering eccentricity. With small, okay, small losses. With large, we have substantial loss. So we are going to be concerned about the moment, this type of moment. So delta times P, that is a moment. So the delta times P, this P times this delta. Okay, it's a moment. So for and restraint, fixed. Okay. For example, we have this figure. Okay. So we have fixed and here, then given the force, compressive force. Okay. Set up equilibrium and solve similarly to Euler buckling derivation. Determine a K factor. So now we will involve a K factor. Okay, so because initially on the original derivation is pin connected. Now end fixed. So if the end is fixed, there's something that we need to involve. So K factor. Okay, so we have this formula, but as you can notice, we have 4, okay, because of the fixed. So we only have this one, KL, because of the factor K, so the effective length. So KL is the effective length. So the effective length will be this portion only. Okay, and because of that, actually, this is actually L over 2. So load strength 4 times as large. Okay, so because it becomes fixed rather than pin connected. So times 4 because the effective length will become 1/2. Okay. So effective length is equal to KL, length of equivalent pin, ended column with similar elastic buckling load, distance between points of inflection in the buckled shape. Okay. So take note, that is the effective length, KL, instead of L alone. So take note L if the end points are pin. So if fixed, we have several types. Okay. So effective length is the distance between points of inflection. Take note, inflection. So this is the point of inflection. Inflection meaning it changes the trend, changes the trend. Okay, in calculus, changes the trend from positive to negative slope. Okay, so that is the definition of inflection. So it is also the length of equivalent pin-ended column with similar elastic buckling. Okay. So we have K factors, equivalent length. Then let's go to inelastic material effects. So about this type of materials. Okay. So we have the stress strain curve. We have the yield stress. Okay. Then we have the modulus of elasticity, and we have this curve. Actually, so ideal. So this is the actual. Okay, so ideal and theoretical. Okay, so tangent modulus. Okay. What about stress versus the slenderness ratio? This is slenderness ratio KL over R. So L over R is the slenderness ratio for pin-ended members. But if the member has several, so to generally introduce K for different types of end connection. For example, fixed-ended connection. Okay. So elastic behavior, Euler stress. So again, pi squared E over slenderness ratio squared. Okay. So as you can see, we have what? Fy minus F residual. Okay, so we have this line. Below that, of course, we know elastic. So above that, that is inelastic. So all of these are the Euler diagram. Euler diagram here. But here, this is what? FC. Okay? Tangential. If you use the tangential rather than the elastic modulus, you will have this type of. So this is the diagram for Euler. With this formula, to replace it by tangential, it will become like this. Okay? So going to the yield point. Exactly going to the yield point. So tangential, again, this is the tangential modulus. So this, from this point, Fy minus F residual. So from that point, going to the Fy, that is our tangential. So tangential modulus changes. Okay? It changes. So we have that total. So the inflection point now is this point. So Fy minus F residual. Okay. Two classes of buckling. Okay. So we have elastic buckling. So the modulus of elasticity is E. But for inelastic buckling, we have this tangential. Okay? No yielding prior to buckling because we are still on the inelastic. There is no yielding yet. So Euler is equal to or less than Fy over minus F residual. Okay? Euler predicts buckling. So Euler buckling. Okay? Exactly. But in elastic buckling, so above that, so some yielding, loss of stiffness prior to buckling. Okay, so Euler stress is greater than Fy minus F residual. Therefore, Fc predicts. So Fc predicts, not Fe. Okay, so this is Fc and Fe. So what can we say about that? Fc means inelastic. Inelastic Euler buckling. So Fe is Euler buckling. So next we have overall column strength. Okay, so for overall column strength, we have the following diagram. So experimental data is the gray the gray shaded region. So Euler, as you can see, so Euler is really the maximum, even in actual experiment. So the Euler derivation, the Euler formula exactly became the maximum. Okay, as shown in the experimental data. Just before buckling. So after buckling, so immediately it will become like this. So there's a very the accuracy and precision of the formula representation, the model is being shown here as really accurate. Okay? Really accurate modeling. So you can see, this is the actual experiment, as you can see. And this is the equation that predicts, this is the equation that predicts, that models the actual happening on the element. So it's very precise. Okay? It's very precise. Therefore, when we are doing still design, it can be very precise, can be very accurate. Okay. And as you can see in details, so inelastic material effects, okay, including residual stress. So we have now the residual stress. That's why it suddenly we have changes here. So the changes are not smooth like this. There is a corner. So it is not smooth. Also here, there are corners. So the what? There are still additional research, additional experiment to be done, but as the current state of knowledge regarding still behavior, okay, it's very much high level already, very high, okay. For example, compare this to our current knowledge on concrete and timber. Concrete and timber has a lower degree of accuracy with respect to what model and formulas like this. Okay? Out of straightness. Okay, so this part. Okay, so because of that, major factors determining strength, we can therefore conclude slenderness, okay, and restraint. So that will give us the key factors. So adding both 1 and 2, so we have what? KL over R. Okay. Number 3, initial crookedness or load eccentricity, of course. And then number 4, prior yielding or residual stress. So this 4. So initially we already know about number 4. And then number 3. Then on this present module, we learned about 2 and 1. Okay. So there is a concept of slenderness, there is a concept of dependencies regarding and restraint. Okay. So all in all, we have 4 major factors that determines strength of the member. Okay. The latter 2 items are highly variable between specimens. Okay. So we can, I show you the accuracy and precision in 1 and 2. There are still to be decided with respect to 3 and 4, but we have a very high level of models with regards to steel design. Okay? Okay, with that, we are through with our discussion of theoretical underpinnings with respect to our global buckling. So, therefore, we must proceed to the global buckling according to the code, according to the manual. So, AISC manual 15th edition. So, AISC 360-16. The same courtesy would be given to AISC, American Institute of Steel Construction, particularly to the developer, Professor Scott Sibian. So here we will have the global buckling slenderness. Okay. So compression strength. Okay. So, here the code gives us compressive reduction or phi sub c is equal to 0.9. So if LRFD is 0.9, of course the factor in ASD is 1.67. We already know that. Okay. Compression strength specification considers the following type of conditions: flexural buckling, torsional buckling, flexural torsional buckling. So combination. So we tackled flexural, then torsional yet, but flexural buckling. So, but they are being defined and suggested from the code. Okay. Compressive strength. The following slides assume non-slender plans and web section and doubly symmetric members. Okay. Compression strength, since members are non-slender and doubly symmetric, flexural or global buckling is the most likely potential failure mode prior to reaching the squash load. The squash limit state is our concern, and the most likely in this regard if we have non-slender. So meaning non-slender, so the L over R ratio is not too high. Okay? So buckling strength depends on the slenderness of section, defined as LC over R. So LC is the effective length of the member. So just like on the theory, LC is actually KL, okay, with the introduction of the K factor for the end restraint. In the manual, the code, the nominal strength is defined as P7 is equal to FCR multiplied by the gross area. So, if LC over R is less than, so take note of this, the threshold is 4.71. Now, LC over R is less than 4.71 or equal to 4.71 times square root of E over Fy. Okay, take note, E over Fy. So we always have to take the square root of E over Fy. Okay, take note that E and Fy both have the same unit. So it will cancel out unitless square root. So we are just taking the LC over R, also unitless because they have the same unit, inches, or feet. Okay. So then, if that is the case, FCR would be equal to quantity 0.658. So you have to memorize this. 0.658 F exponent Fy over Fe. You notice you still have to compute Fe or the Euler buckling. Okay? Or the elastic Euler buckling. So Fy over Fe, so that quantity multiplied by Fy. Okay? Take note, you have the equation 1. Okay? Then you have the equation 2. Then for equation 3, if LC over R is greater than 4.71 square root of E over Fy, then the FCR would be different. So 0.877 Fe. So simpler. Okay. So this is what for what I think this is for, this is non-slender. I think this is also non-slender, but this is greater, no? So the slenderness ratio is a little bit higher here. Okay. This defines the elastic buckling limit. Okay. With a reduction factor 0.877 times the theoretical limit. So the theoretical limit, okay, Fe, of course, that is the maximum theoretical limit, as we already shown you. Okay, but here we are using Fy multiplied by this. Okay, so Fe is equal to elastic Euler buckling stress. Again, we already know this from previous slides. Okay. What about for inelastic materials? Okay. So again, we have the same. So what happens? So we already know this from the theory. So we tackle this from the theory. We already. So it supports the theory, no? The code, the manual suggests the theoretical discussion. Okay. So now it is a little bit different. It is now a little bit different because we have what? Take note of this. 0.44 Fy. Okay. So in the theory, we have Fy minus F residual. So we have what? 0.44 Fy. Okay. Another thing, we have FCR right now. Okay. Critical. So we have critical stress. Okay. That is a little bit lower than the Euler's because of this. So 0.877 Fe, that is the value. Okay. Okay. So on FCR at this point, okay, this point, okay, but up to this point we have another. Okay, so at this point, okay, okay. So where do we find the 4.71? This is the 4.71. This line. This line is 4.71. What is that? 0.471 here. 4.71 square root of E over Fy. That is the line. This is the line. 4.71 square root of E over Fy. Okay. So meaning the theoretical diagram is now having labels, not only labels, but actual equation, okay, with maximum, that is theoretical, but now we have the equation of actual practice here, this one and this one, with respect to the threshold 4.71 square root of E over Fy. Okay? Okay, understood? So this is the threshold that separates inelastic and elastic. region. Okay, so inelastic, this one elastic. So design aids, meaning it could be useful. Table for das 14. So multiply compressive reduction factor with FCR, critical strength. So we have this table. So tabulated values available from the code. It is useful for all shapes, larger slenderness ratio value controls. Okay. What about table 4.1 to 4.12? So also we are multiply the reduction factor. What is the reduction factor? 0.9. Okay. Nominal times nominal. So function of LCY. So LCY meaning this is the effective length in the y direction. Okay. Can be applied to LCX by dividing LCY by, so just by multiplying the gyration. Okay, gyration. So those are still available from the table. Okay, so this ends our discussion of the global buckling. The first topic in in our assumption of the theory and manual in compression methods. Okay. If there are no questions, we will end our discussion right here. Again, this is Dr. AP, preaching engineering for nation building.